Okay, well, thank you very much. And I first want to thank the organizers for this really interesting workshop and the invitation to speak here. It's been very interesting so far. Because I want to talk about some joint work with Johannes Flake, who is also here at the conference, and Sebastian Posur from University of Münster. And this is in progress, but I think the first part of it is very close to completion, so hopefully this will come up very soon. Now, I want to first give a bit of motivation and background on why are we doing this, and then I want to explain the key ingredient in the construction, which is some natural isomorphisms, which we call projection formula morphisms, that are sometimes invertible. Then I will explain how those lead to functors on Drinfeld centers. Then there is a bit of a digression onto well-known adjunctions that are not normally monoidal, but that can be made monoidal under some of the setup we use here, and what is their meaning in this context. So as sort of concrete classes of examples, we can look at functors on yet a Drinfeld module categories, corresponding to extensions of Hopf algebras or morphisms of Hopf algebras. And then I want to give a brief outlook on some of the related aspects of this project that I will not be able to talk about today. Okay, please feel free to stop me with any questions as we go along. Okay, so here's very classical sort of motivation. Let's assume we have a morphism of rings or maybe morphism of monoids even. Of course, we cannot just take this morphism of rings and restrict it to the centers. This just doesn't work. Now, we are very interested in monoidal categories at this conference, specifically symmetric ones. And a ring can sort of, or maybe a monoid, can be replaced by a monoidal category, which is a categorical analog. Of course, things are much more complex here. And then good analog of the center is the Drinfeld center construction, which I think has come up a little bit in this conference, but was not really explained in detail, I think. So I will briefly explain later the definition of this, but I think I believe most people are very familiar with this. And then there's a morphism of rings, has an analog of a strong monoidal functor between monoidal categories. That means we have natural transformations that I want to call Lux and O-Plux. And of course, for a strong monoidal functor, these are mutual inverses, and they satisfy some coherence conditions. And our result can be stated roughly like this. If we take a right adjoint of such strong monoidal functor, then this oftentimes induces a braided Lux monoidal functor between Drinfeld centers. Right,
so one of the points here is that the Drinfeld center construction is not functorial with respect to, like I get a functor from G to D, C to D doesn't mean I get a functor from Z, C to Z.
Yes, yeah, you do not, yeah. There is a construction by Liang Kong, but it uses a different sort of two category of monoidal categories where you don't use functors, monoidal functors, you use categorical bimodules and such. But yeah, that's more of a Morita construction. But if you just think about strong monoidal functor, yeah, you cannot induce it to the Drinfeld center, it just fails. And it already fails for monoids. Yeah. So it somehow came as first, it was a bit surprising that the right adjoint can, however, induce functor. But of course, the right adjoint is in general not strong monoidal. It's just Lux monoidal, which is a weaker sort of condition, where you don't have this natural transformation the other way back in general.
And this functor goes kind of in counterintuitive direction. Yes?
It goes, yeah, it goes.
Well, because you use that adjoint.
It goes in the other direction, but it also is compatible with composition. Okay, so here's some motivating examples of why did we look at such thing, or why did we sort of think this might be possible. So the first example came from finite groups. We can take inclusion of finite groups. And here for later, there's notation of a three co-cycle. But first of all, one can construct a functor and this functor is basically modeled on induction, or co-induction, if you like. And such functor, one can also twist this by a three co-cycle and get a functor on center of vect H twisted by a three co-cycle. So, and this comes from some earlier work with different collaborators. And what we were able to show is that these functors are not just Lux monoidal, they are in fact Frobenius monoidal. That means they also have oblux monoidal structure. Because it's not on the slides, I will briefly say here what Frobenius monoidal functors, but it doesn't play a key role in the talk. This talk is not about Frobenius monoidal functors, but they were somehow what we really wanted to get. So we have Lax monoidal structure and Ob-Lax monoidal structure, and they could be inverse to one another, but they could also be Frobenius compatible, kind of like multiplication, co-multiplication of a Frobenius algebra. And that's a Frobenius monoidal functor.
So can you tell what this functor does when H is trivial subgroup?
When H is trivial subgroup, it sends tensor unit to just the group algebra,
Group algebra is
a joint action, with a joint coaction, yeah, with conjugation coaction. So in general, this is an induction functor.
The group algebra, I guess G in that case, yeah. Okay.
Yes. Yes. So and there was another example which is closely, yeah, and then what we use this to recall results that were due to Davidov and Davidov-Simmons on classifying certain types of algebra object inside of center of such categories. That's a question motivated maybe from conformal field theory. One wants to classify particular type of algebra, commutative algebra objects inside of centers. And Davidov had an idea of, well, if you take one, you somehow identify a subgroup, and really your object is induced from the subgroup. And in the formalism of this functors, one can recover such classification and generalize maybe to prime characteristic or something like that. Okay, another set of functors that we had, in fact, they're closely related to the ones from the groups, are relevant to Deligne categories. And Deligne categories map ST. And these functors are based on induction functors of Deligne categories due to, I think, Etinghoff. And in joint work with Johannes and Nate Harmon, who's also here, of course, we constructed such induction functors and showed that they're also braided Frobenius monoidal functors. And the application of those functors was to classify indecomposable objects in center of web ST. So we were wondering, is this a coincidence that such functor exists? Maybe it exists for more general monoidal center. This is the starting point of the project. Okay, so these are some motivating examples. And now a little bit more background on the Drinfeld center. What we need here is the generalization of Drinfeld center to bimodule categories. So this, I think, maybe this first appeared in Gilaki-Naidu-Niksic's paper, but was also worked out later by Greenock in the thesis and some papers. And here we take a bimodule category over C, and the center has objects given by pairs of an object of the bimodule category together with half braiding. And half braidings have to satisfy compatibility with the tensor product. Here I'm ignoring the natural constraints of a bimodule functor, which do exist here in this categorical language. So basically, there's a condition how you get the half braiding on A tensor B out of that for A and B. And then morphisms very naturally are just morphisms in the underlying category which interchange these half braidings.
So can I ask about previous slide quickly?
Yeah.
So decomposable objects. So when you take the Drinfeld center of a symmetric category, you can think of it as modules over a function algebra on the fundamental group. And so that's an explicit realization. And then, well, this allows you to also probably classify some decomposable objects. So is it kind of, can you do it in this case also that way?
Well, we didn't work out in detail such description. Yeah, the classification here is a bit different. We somehow parameterize object of the center, somehow from the datum that characterizes objects of web Sn, but you can vary n over all n. So you have somehow a combinatorial description maybe.
Because I'm just saying that there is a general, concrete description of the center of a symmetric category. Might apply to other examples. I don't know.
Yeah, maybe. Yeah, we did not follow such approach.
So just a language question about this.
Yeah.
That category is semi-simple, the Z rep ST? So in other words, indecomposable is the same as simple or no?
So this category can be non-semi-simple or semi-simple.
Okay.
In most cases, it looks very similar. Oh, are you asking whether the center is semi-simple?
Yeah.
This question you can also answer.
I guess I'm thinking about, like, am I doing some classification of indecomposables in some finite non-semi-simple setting, or am I just classifying simples? But you're saying sometimes you're literally classifying indecomposables in a non-semi-simple category.
So these categories are semi-simple if and only if rep ST is semi-simple, and the center is semi-simple we can derive from interpolation category techniques.
Oh, the center is semi-simple?
The center is semi-simple if and only if the underlying category was semi-simple. So when T is generic. So yeah, so this is so whenever you know that rep ST is semi-simple, then also the center is semi-simple and vice versa. And we did not know that before using interpolation techniques, but yeah. Okay. So yeah, here's a few special cases of Drinfeld centers of bimodule categories. Of course, you can take the regular C bimodule, where the action is just a tensor product. In which case, you just recover the definition of a Drinfeld center, which is a braided monoidal category. Then you can also consider a monoidal functor, and such monoidal functor makes D into a C bimodule, somehow along restriction. And then you still have a monoidal category. In general, the center of bimodule category is not monoidal, it's just a category. But in this case, it's a monoidal category. This was already known to Majid in the early 90s. And what is actually interesting about the center of bimodules is that if you have a functor of C bimodules with fixed actions from a fixed category C, then it induces a functor on bimodule centers, but also a bimodule transformation gives natural transformation. So this is in fact two functorial. This was already observed by Shimizu, but maybe it's more widely known. I don't know. So this is going to be a tool for us at some later stage. Okay. Now I want to talk about monoidal adjunctions. And we give a bit of a sort of formal framework to look into this. In order to do that, I want to consider two categories called cut-lux. And here objects are monoidal categories. So by the way, we don't impose restrictions on monoidal categories here at this point. You can, of course, put your favorite restrictions of tensor category, maybe K-linear or abelian if you like, but it's not necessary. And here one morphisms are Lux monoidal functors between monoidal categories. And two morphisms are monoidal natural transformations. So these are compatible with the Lux structures. Here, I'm just putting diagrams for monoidal natural transformation of Lux monoidal functors. So it's a very natural assumption that the natural transformation basically on the tensor product is the tensor product of the natural transformations on the objects, roughly speaking. And now we can say that a monoidal adjunction is just an internal adjunction in such category. Okay, so this is what we call a monoidal adjunction, but what does this mean in practice? I mean, there's a well-known result that, okay, let me mention this first. So if you have a monoidal adjunction, then in particular G becomes strong monoidal. And this is because R is Lux monoidal by assumption, but then the left adjoint of a Lux monoidal functor is Ob-Lux monoidal. And it in fact follows that it becomes strong monoidal here. And also you can say that if G is strong monoidal, there's a unique Lux monoidal structure on R such that you have a monoidal adjunction. This is the old result from category theory, but here we formalize it a little bit in this two category. So this is what we want to look at. So most of this paper is in a setup in which you have an adjunction where the left adjoint is strong monoidal, right adjoint is Lux monoidal. Okay. Now I want to introduce the main sort of players in the construction, which we call projection formula morphisms. And those are basically natural transformations that are built out of adjunction data and monoidal data. Okay, here we describe how the left version of that is defined. So we can, if we start with A tensor Rx, we can apply the unit of the adjunction, and then we can apply the Lax monoidal structure of R. And the resulting thing is a natural transformation that somehow takes this R of X, takes R outside on the price of having G applied to A here. So this you can always define for monoidal adjunction, or even slightly weaker. And there's a analogous right version of this, where instead of having A on the left, you have A on the right. So there's basically just a completely analogous right version of this natural transformation. And we say that if both of them are invertible, we say projection formula holds for the right adjoint. It's somehow a property of right adjoint. Oops. Okay, now this is familiar from different areas of mathematics, this sort of isomorphism condition. For example, in representation theory, sometimes could be called Frobenius reciprocity. So we have an inclusion of finite groups. Now I'm lying here slightly because in this adjunction, the right adjoint is the strong monoidal one. So somehow this is opposite, like it's happening in opposite categories, but that's fine. Maybe we call this op-monoidal adjunction. And then one has natural isomorphism between induction of restriction tensor W and V tensor induction of W. This follows from Frobenius reciprocity. But also in algebraic geometry, if we have morphism of schemes, we can look at inverse image, direct image. Here, inverse image is strong monoidal. Now we can take quasi-coherent sheaves maybe, but let's say one of them is locally free, and then one also has such isomorphism. Here in algebraic geometry, the tensor product is relative over a rank of functions, so it's a bit of a different sort of flavor of tensor product and representations of groups. But there's an analog sort of morphism, and here I think in algebraic geometry people call it projection formula. And so that's
one being invertible does not imply that the other is invertible. Is that right?
I think not in general, but in braided or symmetric monoidal categories it does. Yeah. You can use braiding to show if one is invertible, the other one is invertible. Okay, so here's a bit more of an example that's a little bit out there because it doesn't use any linear structure. But we can have categories with finite products. We can make them monoidal categories with Cartesian product. And we say they're Cartesian closed if taking the product with A has a right adjoint, something like an eternal Hom object. And the functor that preserves such products and has a left adjoint can be used to build an op-monoidal adjunction. Here that means that here G is the strong monoidal functor and the left adjoint is op-Lax monoidal only. So this is a type of situation one can consider, and now we can call such functor G Cartesian closed if it preserves these right adjoints of tensoring. This is an additional assumption. Not every product-preserving functor does this automatically. And if that's the case, then that's actually equivalent to the projection formula morphism being invertible here. And in this setup, the projection formula morphism is just something you get naturally out of universal property of product objects. And this is, for example, written in Peter Johnston's book on Sketches of an Elephant. So this is also an example. Although here maybe the Drinfeld center is not very interesting for such categories. So we see like this projection formula morphism does appear in different contexts. And here's a proposition, sort of a sufficient condition of when is it invertible. Well, if you have dual objects, like a rigid category, then projection formula morphism is always invertible. For the context of symmetric monoidal categories, this was proved by Faust, May, and we noticed that it's not necessary to have symmetric monoidal structure here, but it just works in general. But it is more general, so we know examples of functors where projection formulas hold, but they're not rigid categories. So this. Okay, so now, in order to induce functor on Drinfeld center, we want to use the projection formula, and the key sort of observation is that if it holds, then we get a morphism of C bimodules from modeled on the right adjoint. So maybe I recall here that we have G going from C to D. This is strong monoidal. And then there's a right adjoint, which is Lax monoidal. Now, this functor goes from D to C, But in fact, with the projection formula morphisms, we can make it a functor of bimodule categories. We need to let C act on D using the strong monoidal functor, and then there's a lot of coherences to check, and we check a lot of coherences, but it is true that these projection formula inverses can be used as lineators or associators for bimodule category structure. And this is very good because we observed before that taking centers of bimodule categories is too functorial. So if you put in an adjunction, you get an adjunction out of it. If you put in a monoidal adjunction, you get monoidal adjunction out of it. And this is what happens. So we have a monoidal adjunction of C bimodules, and then it gives one of categories if we apply bimodule center to it. And this is very close to being induced functor on the center. It goes from a center of the bimodule category DG to center of C. So now all we need to do is somehow start at the center of D rather than center of D acting through G. But that step is not difficult because the center of D is contained in center of DG as a monoidal subcategory. So this is somehow the next step. Okay, so here we use the two functoriality of taking bimodule categories center. So now we can compose. We can first include the Drinfeld center of D. So this is the braided category into a category that's not necessarily braided, but monoidal. This is a monoidal full subcategory. And then we apply this induced functor to get to the center of C. So here to just recall, this is well-known functor from CD into CDG, which instead of evaluating half braiding on anything, it just evaluates half braiding on objects of the form G of an object. This is a bit of something like a forgetful functor in some sense that restricts the half braiding. And then we can prove that if you have a monoidal adjunction and it satisfies the projection formula, then we in fact get a braided Lax monoidal functor on the centers. For braided, we need to do some little bit of extra work to check compatibility with the braiding, but it also works. And here, one can display what happens to an object. So an object in a Drinfeld center is a pair of an object and a half braiding. And then under this functor, we again get a pair of an object, which is R of X, and a half braiding. And the half braiding uses projection formula isomorphisms to conjugate and applies R to the half braiding that we had. And then the Lax structure is just inherited from R. That means the existing morphism Lax R happens to be a morphism in the center with respect to these half braidings, which is some further coherence condition one needs to check. Okay, but this is essentially the construction. Okay. Are there any questions at this point? Okay, so I think the rest of the talk I want to spend with two things. I want to discuss Kleisli and Eilenberg-Moore adjunctions because they can be made into monoidal adjunctions. And I want to present some examples from Hopf algebras. Yeah?
So say I'm in the case where I have a surjective Tensor functor from C to D. My induction, say I'm in some symmetric or braided case, my induction should be some particular algebra object, induction of one, some particular algebra object inside of C.
Yeah.
And then I could consider like the monoidal category of modules for that algebra.
Yeah.
Or I could put that algebra inside of the center as long as I'm commutative. It looks like maybe I would be monoidal if I instead go to the category of modules over that algebra object.
Yes. This will come up when looking at this Eilenberg-Moore type of categories. So I think this sort of thing will appear there very naturally. Yeah. Yes. So, right, indeed, it was known before that right adjoint applied to unit object is a commutative algebra in the center. And you can study its modules, which is a monoidal category. So we'll come to this later, I think. Okay, so here's a corollary, which is a clear corollary that such functor, because it's compatible with braiding and has Lax monoidal structure, preserves commutative monoids, which is a sort of a motivating corollary to consider such thing. And here's some first examples where we have the finite group situation. We consider restriction functors, but then co-induction and induction here for finite groups happen to be isomorphic, so we can model the right adjoint on induction, which is a bit easier to write down. Now the center of representations of G is a Drinfeld module category. So basically here, it can be described by saying these are representations of H together with a coaction or grading by the group H, and then they have this conjugate compatibility.
There's some confusion between G and H here.
Oh yes, that's right, there's a typo here, yeah. So this should also be an H. So I was writing this for H because I wanted to input such object into Z of R. And then here one can see that it's an induced module. And the coaction just very naturally, kind of, if you just wanted to by hand try to write down yet a Drinfeld module structure on this induced, well, this is what one would guess, because one has to conjugate by the yet a Drinfeld condition. So this is what happens. And this is what the functor evaluates to for the group case. Okay. Now, from this, it's a bit of a slight change of topic to consider monoidal monads and Eilenberg-Moore categories. So a monoidal monad here can be formalized as just being monad in this category of monoidal categories with Lax monoidal functors. So this means concretely you have a monad on C. C is a monoidal category, and then T is also a Lax monoidal functor in such a way that unit on multiplication are monoidal transformations. And one can show that very naturally, of course, if you have a monoidal adjunction, then the corresponding monad is a monoidal monad. Now, here I want to recall some work that goes back to Schauenberger, but also Pareges, on commutative central monoids, or often people call this commutative algebras in a tensor category, in a braided tensor category. So here, let's say C is actually not braided yet. You can still define what is a commutative monoid, and we call it here commutative central monoid if it's a commutative monoid inside of the center of C. That means you have some multiplication, some unit morphism, and these are morphisms in the center. Now this can be used to construct a monoid by tensoring. Right, you can just tensor with such commutative central monoid, and you have a monoidal monad. In fact, because it has a Lax structure, the Lax structure one can write explicitly here, but maybe this is a technical detail. But because we have half braiding, which I'm actually writing with C here, so that's a bit of a mismatch of notation. So you can use the half braiding and the multiplication to produce Lax monoidal structure for the monad. And one can show that if you have such commutative central monoid, in fact, Tm becomes monoidal monad. Okay, so the reason I'm mentioning this is because there was a second interpretation of the projection formula morphisms, namely that they give isomorphisms of monoidal monads. So here's the statement. Let's say we have some monoidal adjunction, but it satisfies projection formulas. So the projection formula morphisms are invertible. Then we can use the commutative central monoid of applying R to the tensor unit. And that's a commutative central monoid, which is known. And then the projection formula isomorphism evaluated with fixed object tensor unit in the second component is an isomorphism of monoidal monads. So this is the second interpretation. Our first interpretation of projection formulas was that it gives C bimodule morphism. Here the second interpretation is that it gives some isomorphism of monoidal monads. Okay, so here's a short example. Again, we look at groups. Then R of 1 is just some kind of function algebra on quotients on the set of cosets. Such algebra was, I think, used in Kirillov-Ostrich, and one can show that, in fact, modules over such coset algebra is just representations of smaller group. So, and we will interpret such result in more generality here. Okay, so now one can now use this, and I need to be a little bit cautious about time. Okay, yeah, I think one can now use this to define monoidal Kleisli adjunctions. So the Kleisli category of a monad has the same objects as the underlying category C, but morphisms are given like so. But the best way to think about this is as free modules over T. And then you have a diagram of functors. So here's the original adjunction GR. And then the Kleisli category has its own adjunction with a free and a forgetful functor. Here you just forget the action of t, and here you just have a natural sort of monoidal natural functor of free modules. So now if you have a monoidal monad, then one can, without further assumption, show that the Kleisli category is also a monoidal category. And the tensor products here are the underlying tensor products of objects in C. So nothing changes. In some sense, maybe as a quick explanation, this is something like if you have free modules over some monoid object M, and if you took a relative tensor product with M, this ends up being isomorphic to the tensor W, tensor M. So for free modules, even if you take relative tensor product, it's really just tensoring the coefficient module, let's say. And then here, tensor product of morphisms formally applies Lag's monoidal structure of T. Okay. So now there is a universal property that translates from usual Kleisli adjunction to monoidal adjunction now. So if you have a monoidal monad, one can write such an adjunction. It's a monoidal adjunction. And it's also initial among monoidal adjunctions. So this means that in this previous slide, there's this induced functor G tilde. And it goes out of the Kleisli category. And this means that this adjunction here, the free forgot adjunction, is initial. If you had any adjunction GR that composes to the monad T, you always get a morphism between from that free forget adjunction to this GR adjunction. So in some sense, the Kleisli categories and its adjunction are initial for a fixed monad T. And now this is just a universal property for monoidal adjunctions. And there's also a characterization theorem, which maybe is a little bit surprising, but if we have monoidal adjunction and the projection formula holds, then it also holds for this right adjoint functor forget. So we have the Kleisli adjunction, its right adjoint is the forgetful functor, and it also satisfies projection formula as soon as R satisfies it, so it's just automatically inherited. And now if G is also essentially surjective as a functor, then the comparison functor becomes a monoidal equivalence. So it's enough for then, under the assumption of projection formula, if we also have an essentially surjective functor G, then your category is already equivalent to a Kleisli category, which is something like free modules over R1, in fact. So because the other result said that the monad T is actually isomorphic to tensoring with R1, so an interpretation of this equivalence is now that under the assumption of G being essentially surjective, that the category D becomes equivalent to something like free modules over R1 inside of C.
In the essentially surjective case.
In the essentially surjective case, and the projection formula also has to hold. So these are two assumptions, and those two assumptions then suffice. But this is not just the monoidal equivalence of monoidal categories. This is in some sense an equivalence of monoidal adjunctions, but that's a little bit more technical to formulate, I think. So I will. So now here's an example. Let's take a finite dimensional Hopf algebra. And we have the fiber functor going to vector spaces. This is a strong monoidal functor. It's also essentially surjective, of course, because you get the simple object is in the image. And the projection formula holds because we observed earlier if the categories are rigid. Well, this category is not rigid technically, but the projection formula still holds, which we can show by invertibility of the antipode. Now then, R1 is H star, is some structure of commutative central monoid. And the characterization theorem implies that category of vector spaces is equivalent to the Kleisli category of H star. But this you can see as free H star modules inside of H mod. And this is now a familiar thing, because one step in proving fundamental theorem of Hopf modules is to show that every Hopf module is free. And then that the free Hopf module is equivalent to category of vector spaces. So an example is this, and then you can do this slightly more generally. Take finite dimensional braided Hopf algebra inside of the Drinfeld category. Take a byproduct, which is a Hopf algebra, Now we can restrict from modules over the biproduct to K mod and build a monoidal adjunction. And then this also ends up essentially surjective, because here we have a Hopf algebra with a projection. So every K module can also be induced to an H module. So this is an essentially surjective functor. And therefore, K modules is equivalent to 3 B star modules inside of H mod. So this is a variation of the, I mean, this is probably also quite well known from Hopf algebra theory, I think. So it's a variation of this fundamental theorem for Hopf modules relative to K mod, I guess.
So question. So I think you wrote a few years ago, maybe more than a few, a paper about taking quantum double of a Hopf algebra in a braided tensor category. So this is about this, right? It's another instance of this story.
You mean the second example here? Oh.
Well, it's yeah. In this case, it's in a braided tensor of yet instant module, but in general braided category, you can take quantum double. And this is an instance of your construction.
Yeah, it probably is related. On the
So
spot,
you can
not
take
quite sure.
quantum double in a Drinfeld center of another category.
Yeah, roughly speaking, yes, yeah. Yeah. So this is in some sense related, but I'm right now not sure about exact relationship, yeah. Yeah. That's right, yeah. Okay, so, well, if there are no further questions at the moment, I will move on to briefly discuss monoidal Eilenberg-Moore categories. But here we are slightly cheating. And the way we are slightly cheating is we use this isomorphism of monoidal monads. So in fact, under projection formula, our monoidal monad is just tensoring with R1. And that makes life a lot easier to define Eilenberg-Moore category, which in general is very technical, I think. So, and the idea here is somehow the Kleisli category corresponds to 3 modules of an algebra object, and then Eilenberg-Moore category would be all modules. So if we have the projection formula holds for a monoidal adjunction, then we have this isomorphism of monoidal monads. So instead of trying to think about the Eilenberg-Moore category for T, we can just think about modules over R1 internal to the category. So all of the Eilenberg-Moore categories are really given by mod Cm, so internal modules over M inside of C. Now here, in this category was studied by Schoenberg, and
so Eilenberg is a mix of Eilenberg and Schoen, yes?
Yeah, oh sorry, that's a typo, yeah. Yeah, I should have searched that because I'm sure it's gonna make that typo, yeah. Okay, yeah, this is of course very intentional, yeah. Okay, so here, I mean, one might wonder how is that even a monoidal category if you have not seen the construction of Schoenberg. But the way this can become a monoidal category is just sort of using that C is in fact an algebra object in the center of C, but I think this is on the next slide. So here, just as a category, the Eilenberg-Moore category then consists of right modules over internal to C and morphisms commuting with the actions. And in general, there's a paper by Seal that tries to, in complete generality, define monoidal. Well, there's technical assumptions under which we can get monoidal structure and Eilenberg-Moore categories, but we don't really need this here. And in a special case, it will coincide. So now, how does this become a monoidal category? Well, we need to make a technical assumption. Minimal technical assumption is that C has reflexive coequalizers and that the tensor product preserves them in both components. So this is right exactness of the tensor product, but it's really the minimal thing one needs. And then one can make modules into a monoidal category with relative tensor product. Relative tensor product is a coequalizer of acting and acting here on the right on B, on the right on A, or acting on the left on B under use of this half braiding. So in this way, Schoenberg showed, first of all, that this gives a monoidal category. In particular, one can build a monoidal Eilenberg-Moore adjunction out of this. There's a free functor, there's a forgetful functor again. And now, under the same technical assumption as before, there was a universal property for this Eilenberg-Moore adjunction as well. Namely, if the projection formula holds, we need to assume that, then we can work with commutative central monoids. Then it also holds for the right adjoint of the Eilenberg-Moore adjunction. And there is an induced functor in the middle here, And this functor somehow makes the Eilenberg-Moore category terminal because it goes into it. So in some sense, Eilenberg-Moore junction is terminal, Kleisli junction is initial, for monoidal junctions as well. So this is, one can show. And one can also derive a crude monadicity theorem. Then we need to, crude monadicity will address the question of when R tilde is an equivalence of categories. And the minimal assumption, not minimal assumption, but one assumption that's sufficient is to say R here needs to reflect isomorphisms, and I think all of these functors need to preserve reflexive coequalizers. For one of them it's automatic, for one of them it's not, and then you actually have the result that D is equivalent to modules over M. So I think this answers Chris's question from earlier. So, well, and so under certain assumptions, you just get that the target category is equivalent to modules over R of 1, but not always. And now we want to consider the center, and there is a result, nice result, describing a center in terms of local modules. So first of all, local modules are a way to produce a braided monoidal category of modules over an algebra object. This is due to Bodo-Pareigis. If we have a commutative central monoid, we can look at, it's in commutative algebra in the center, so M actually is in sort of a commutative algebra in the center, so we can consider modules over it internal to the center. This is also a monoidal category. In fact, then if you restrict to special modules called local modules, it's a braided monoidal category. And local modules basically, so if you have, here we start with right actions. So graphically you have somehow a right action on an object. Now if you want to turn this into a left action, you have two choices in a braided non-symmetric category. You can either braid above, or you could braid below. And local modules don't see the difference. And this is how they can become braided monoidal category. So this is the old result of Bodo-Pareigis, that this is a braided monoidal category. And then there's a very nice result of Schoenborg, that there's an equivalence of braided monoidal categories between the center of modules over internal to C and local modules internal to the center. Okay, so I'm mentioning this because the main sort of construction here is an induced functor on centers, on Drinfeld centers. And in this case of Eilenberg-Moore category, we can recognize what the functor is. It ends up just being a forgetful functor for local modules. So now still we have the standing technical assumption on category C, which we need. And now we can recognize that the induced functor of the right adjoint of the Eilenberg-Moore adjunction induces braided Lax monoidal functor that goes from the center to center of C. But under Schoenborg's equivalence, that this functor is the forgetful functor, forgetting that you have a local module. So this functor we know, it can be recognized as the forgetful functor in a special case where your category is of Eilenberg-Moore form, it's the forgetful functor on local modules. And then the Lax monoidal structure is the co-equalizer morphism of relative tensor products. Okay, so now, yeah, somehow my color has changed again.
Maybe your battery is losing power.
I think it's...
It thinks it's nighttime.
Yeah. Okay, sorry about that. Okay, so yeah, this is an instance of these center functors, the forgetful functor of local modules. But now other examples can be studied by considering yet a Drinfeld module categories. So here we go to Hopf algebras. We have a morphism of Hopf algebras. They don't have to be finite dimensional. We also don't need to use finite dimensional modules. We can do this in general. And there's two types of adjunctions one can consider. There is strong monoidal restriction functors for modules or for comodules. Alternatively, we can consider these. And then a comodule injunction will always satisfy the projection formula without further assumption, because the antipodes are invertible. However, module co-induction satisfies the projection formula of H is finitely generated as a left K module, so there's technical assumptions here. Either way, in these cases, one then gets induced functors on the centers, and the centers are equivalent to these categories of Drinfeld modules. So one can write down such braided functors on Drinfeld categories here. This can be made quite explicit, but it's easier to make it explicit not for co-induction, but for the left adjoint of induction, which is an Oplaks monoidal functor. But let's state a few examples. So we can look into the morphism of affine algebraic groups, which secretly is just a homomorphism of Hopf algebras of the coordinate rings, which are commutative. And then one gets a braided Lax monoidal functor. Now, the question is, what is the center of representations of an algebraic group? But this gets an interpretation here of some sort of quasi-Coherent sheaves on a quotient. For me, this is just an interpretation because we can give an explicit module for this category. We don't have to write down a stack, we just say what the category is. The category will be something like internal modules over algebraic group or over the coordinate ring inside of co-modules over the coordinate ring. And then one gets an induced functor there, which is braided Lax monoidal. Yeah, here is an explanation of how the center of rep G is such category. And then here I need to point out that the tensor product used is not the relative tensor product on the coordinate ring, but it's some sort of convolution tensor product because OG has a coproduct, and you can use that to define a tensor product that factors over the vector space tensor product with a fiber functor. Okay, so here's another example, now something with quantum groups. The quantum groups are root of unity with technical assumptions of odd root of unity or maybe not divisible by the order not divisible by 3 if you have type G2. There is a central Hopf subalgebra inside of the quantum group at root of unity. The central Hopf subalgebra can be written as coordinate ring of an algebraic group, and it includes into the quantum group, and it's central in there. It's a commutative central sub-Hopf algebra. So we can apply the induction functor to such pair, such inclusion of Hopf algebras. And then one gets some sort of functor that takes something related to a classical group and produces something, let's say, get a Drinfeld module over quantum group of root of unity. And we do not understand very well what exactly this does for certain modules. This may be difficult to compute, but the image of the tensor unit is the dual of the small quantum group. And that becomes, in a certain way, yet a Drinfeld module over the big quantum group with, I think, a joint action and regular co-action, I believe, or vice versa. Okay, so this is some examples, and maybe to conclude. So, well, we originally started looking at Frobenius monoidal functors because those are the examples we knew. Now and we're still interested in doing that, but to get Frobenius monoidal functor, we have to consider an ambi-adjunction where the left and right adjoint are modeled on the same functor. In such a situation, you will get two projection formula morphisms, one for left adjoint and one for right adjoint. They go between the same objects in opposite directions. If they happen to be inverse to one another, then you get a Frobenius monoidal functor. So this is some work that we are currently writing up. So you can also, under certain situations, which are a little bit harder, get Frobenius monoidal functor, and you can study what this means for Hopf algebras. And then there was also a side project on implications of projection formula for existence of abelian envelopes, which I will not be able to talk about now in this talk, but this is also an application we have in mind because originally we started thinking about this because we were thinking about the center of rep ST, and we found a functor that goes there, and we want to generalize. So we're also interested in how this says something about interpolation categories of a more general nature. Okay, well, thank you very much.